is a force of attraction that exists between any two bodies or masses everywhere in the universe. The Earth is so massive and huge that all the other objects close to the Earth are attracted or pulled towards it. The force which acts between two bodies when the bodies are not directly touching each other is called force at a distance. These forces can be explained by using the concept of a field. Let us do some activities to know more about the forces at a distance. Now, let us perform an activity to visualize the magnetic field. Click each tab to know more. Take a bar magnet. Put it on a table. Take a white drawing sheet. Place it over the bar magnet. Now take some iron filings. Sprinkle them on the paper. Now tap the table gently with pen or pencil. Observe the changes.
Is your phone filling up with photos and videos and feeling slower by the day?
In this activity, we observe that in a small space around the magnet, iron filings set themselves in a pattern because they are affected by the magnetic force of the field created by the bar magnet. So, the pattern represents the magnetic field. The space around the magnet where its influence can be detected is called the magnetic field. Finally, we learned that every magnet has an invisible magnetic field around it. This field is made up of lines of force that attract magnetic material such as iron filings. The filings form a pattern as they line up in the direction of the magnetic lines of force. Thus, we say that a field is a region in which a force can be experienced by another object placed at any point in that region. Practically, many forces can act simultaneously on a single body. For example, consider an object placed on a horizontal floor. In this situation, two forces act on the object, where one is the gravitational force and the other is normal force, which acts vertically downwards and vertically upwards respectively. In this case, the forces acting on the object are equal in magnitude and opposite in direction. Hence, there exists no change in the state of the object. Technically, the net force on the object is said to be zero, as the state of the object does not change. The sum of all forces acting on an object called net force. Imagine that the same object is placed in a lift which is accelerating. In this case, the object is in non-uniform motion. So, the net force acting on the object is not equal to zero. When two forces act on a body, as in the above case, one of the forces should be greater than the other to set the body in motion. The strength of a force is usually represented by its magnitude. The direction of a force is as important as its magnitude. We represent the direction of force using arrows. Now, let us perform an activity to observe the effects of net force acting on an object. Click each tab to know more. Choose a heavy object like a table that you can move only by pushing hard. Try to push it. Observe the changes. Now ask your friend to push in the same direction along with you. Observe the changes. We observe that it is easier to push the table when you take the help of your friend. The force applied by your friend added to the force exerted by you results in both forces being applied on the table in the same direction. The total forces applied by both of you makes it easier to move the table. Now, ask your friend to push the table from the opposite direction to you. Observe the direction in which it moves. We observe that the net force on an object is zero if the two forces acting on it in opposite direction are equal. Finally, we learn that all forces have both magnitude and direction. While adding forces, the directions of forces have to be taken into account. When forces act on a body along a straight line and they are in the same direction, the net force is taken as the sum of all forces acting on the body. The sign convention must be used to add forces. The force F1 directed towards right could be taken as positive and the force F2 acting towards left could be taken as negative. If F1 greater than F2, then net force Fnet is equal to F1 plus minus F2 is equal to F1 minus F2. Finally, we conclude that if the two forces act in the opposite directions on an object, the net force acting on it is the difference between the two forces. The object at rest moves in the direction of the net force acting on it. Now, let us perform an activity to know the effects of stretched rubber bands on fingers. Click each tab to know more. Take a rubber band. Stretch it using your fingers. Observe the force from your fingers. Now take one more similar rubber band. Add it to your fingers and stretch both together to the same length. Observe the force exerted on your fingers by the rubber bands. Repeat the same procedure by increasing the number of rubber bands.
పాలు గోధుమలు మరియు విటమిన్స్ తో తయారైన హార్లిక్స్. ఎప్పుడు ఇంత పెద్దగా ఎదిగావు? కారులోనే కూర్చోండి. ఏం చేస్తున్నావు? నాన్నని చూశాను. ఎప్పుడు ఇంత పెద్దగా ఎదిగావు? హార్లిక్స్ పాలు గోధుమలు విటమిన్స్.
जब लाइफ लगे डल, अपने बालों की शाइन से बदलो कल.
हेयर ड्रेसर्स की जॉब खतरे में? ओह, मेरी जॉब. एक अच्छी हेयर ड्रेसर को पार्लर की नहीं, क्लाइंट्स की जरूरत है. सनसिल्क ब्लैक शाइन विद आंवला पर्ल्स. अब हर वॉश में बढ़ती जाए शाइन. वेलकम टू द फर्स्ट एपिसोड ऑफ श्रेया शाइन ट्यूटोरियल्स. आज मैं आप सबको सिखाऊंगी स्प्लिट एंड्स का दी एंड. मस्त साइड छोटी, ऐसे मोड़ो फिर ऐसे मोड़ो. फटाफट फ्रिंज. जब लाइफ लगे डल, अपनी शाइन से बदलो कल.
श्रेया, तू मैगजीन पे.
सनसिल्क ब्लैक शाइन. दुनिया में छाओ all the time.
We will observe that when we stretch the rubber band, it exerts force on our fingers and feel the force of pull on our fingers. Similarly, we also observe that the combination of two bands exerts a larger force than that of one rubber band. Assume that the force exerted by one rubber band is F units and the force exerted by the second rubber band is F units. Then the net force of two rubber bands is shown on the screen. The unit of force in SI system is Newton N. The diagram showing all the forces acting on an object at a particular instant